Welcome, good day, learners. Welcome to the discussion for Geography Paper 1. Discussion for Geography Paper 1 in preparation for June examinations and also in preparation for the prelims and the final examinations. All right, we are going to do our discussion based on a sample paper, and we'll try to simplify and try to make the questions clear and understandable, and also try to illustrate how we get to the correct answers to the given set of questions. Right. We are going to start with, as usual, we understand, and I think we know, our paper will be comprised of 3 questions, 2 questions in section A and 1 question in section B. The 2 questions in section A, each having 60 marks. The first question is based on climatology or climate and weather. Then the second question would be based on geomorphology. Then the last question is on geographical skills and techniques, which is Mapwork. So we are going to start with the first question, which is a question on climatology. This is question number 1. Right, the first question says, refer to the diagram below, which depicts a valley in the southern hemisphere. Choose a term from column B that matches the description in column A. Write only letter Y or X. Right, so we are seeing a situation here of our valley climate. We are saying this is typical of a valley climate in the southern hemisphere. Right, I will try to illustrate the situation of the valley and the associated conditions in a valley. Right, if we are in the southern hemisphere, this is our north-facing slope. I think you can see, basing on slope aspect, we are saying this is the north-facing slope, or this is our southern slope. Right, and we are seeing that this is our south-facing slope. So based on this argument here of slope aspect, we understand that in the southern hemisphere, it is the north-facing slope, which faces towards the direction of the sun, mainly in our winter season when the sun is low in the sky. So meaning to say it is this north-facing slope that receives insolation, and the south-facing slope, it means it's facing away from the direction of the sun in the southern hemisphere. Right, so we tend to have cool air sinks down the valley slope, like what you are seeing with this arrow, and also we have the sinking air. And you see our temperatures in the valley floor, they are very low, 4 degrees Celsius, which requires the growing of frost-resistant crops and also frost-sensitive crops on this side. Right, and we have warm air displaced upwards. Right, this warm air is going to be displaced upwards because of this cold sinking air. As this cold air is sinking, remember, it's more denser. Because of its density, it means it's going to occupy the bottom of the valley, and it makes the warm air subside. So it's displaced vertically into the upper parts of the valley. And we are also seeing that we have this layer here, which is as a result of the suppression caused by strong descending air. There is cooler air sinking, which is trapping warmer air. Right, so let's go to the questions and try to analyze the questions and try to figure out the best possible responses given that situation of a valley climate in the southern hemisphere. Right, so the first question is saying, the area marked D is this area here. This area that you are seeing, the area marked D, is this area here. Right. So this area here, we are seeing that it's a zone of warm air, which is bound by cold air on top. Remember, we said there's strong descending air, and also we have cold air from the bottom, which has managed to sink into the valley. So there is a belt of warm air, which is trapped in between a belt of cold air and a cold air below. So this one is a belt of warm air, which is trapped between 2 cold air masses. Right. So the best response there for this one our response for layer D is called the thermal belt, which is X. So it's the thermal belt. Right, then we move on to the next question. The dash slope is the cooler. The dash slope is cooler in this valley. Which one is cooler in this valley? We've talked about that. We said this one is facing towards the direction of the sun, and this one is facing away from the sun in the southern hemisphere. North-facing slopes are facing towards the direction of the sun, while south-facing slopes are facing away from the sun. So our correct response is Y. The south-facing slope is the one which is cool. Right. 113. The wind blowing at E generally occurs during the at E. Right, what happens here in the valley? Let me try to illustrate. Let me try to explain on the winds that happen to exist in the valley. Right, we tend to have what you call, I'll illustrate the day situation and the night situation. Right, if this is our valley in the southern hemisphere, we are saying during the day and during the night, we have the situation of what we call the katabatic, and we have what we call the anabatic winds. Right, katabatic, this is a night situation. This wind blows during the night, and this typical wind is a down slope. And anabatic, this is a typical of day situation, and this is an up slope wind. Right, what happens is during the day, let me start with the night situation, or the day situation rather. Let me try by illustrating how anabatic winds form. Right, we said anabatic are upslope winds. What happens during the day is when it's winter, because remember, valley climates are more pronounced during the winter season. Right, what will happen is, let me try to make a clear illustration. Right, this is our valley in the southern hemisphere. We are saying in this valley, we are having the sun, which is low in the atmosphere. It's typically during winter season. The sun is low in the atmosphere, meaning to say the sun will effectively hit the valley sides here. Right. So during the day, we are saying the valley side is being heated by insolation. And remember the relationship between temperature and pressure. Right. When temperature is high, pressure tends to be low. And when temperature is low, pressure tends to be high. Right. So because of this situation, this valley side is heated because of insolation during the day, meaning to say there is a creation of a low pressure on the valley side here because of higher temperatures. The air immediately above here is heated and it rises, creating a vacuum of low pressure around the valley sides. And there is no heat which is being received in the valley floor here, meaning to say it's cooler in the valley floor, and meaning also to say in terms of pressure, there is high pressure in the valley floor. And we are seeing that there's a high pressure cell in the valley floor, and there's a low pressure cell on the valley side. And because of these differences, there's now pressure gradient, which tends to drive the air from the valley floor going upwards. So because of this difference, there's pressure gradient, air tends to move from the valley floor going upwards to the low pressure valley sides. This is typically during the day, what we call the anabatic winds. Then at night, we have a reversal of the system. At night, we still have our valley. Right, this is our valley floor, and this is our valley sides. Right, the side of the valley which was having insolation during the day is going to lose heat at night due to terrestrial radiation, or what we call a long wave radiation. So, but the valley floor is not affected mainly. The conditions in the valley floor, they maintain. This valley side is the one that is most affected by the long wave radiation. It has received heat during the day and it will lose all that heat at night because of long wave radiation. So it implies that the valley side now extremely gets cold and the pressure here becomes higher compared to the valley floor. The valley floor is now warmer during the night compared to the valley side, meaning to say there is now a lower pressure cell in the valley floor and a higher pressure cell on the valley side. And now there's pressure gradient. There's low pressure in the valley floor and there's higher pressure on the valley side, meaning to say the air now will tend to move in that direction from the valley side with higher pressure going to the valley floor with lower pressure. This is typically during the night, and this is what we call the katabatic wind. Right. So we go back to our question and try to relate the concepts to the question and try to answer the question. The wind blowing at E generally occurs during, right? So if we check at E, this is a downslope. We are seeing our arrow is pointing to the valley floor. So when does that happen? When do we have downslope winds occurring in the valley? Right. Our correct response is Y. That is typically a katabatic wind, which is realized during the night. Right, moving on to the next question. The temperature at D is higher because, right, temperature at D, why is the temperature at D higher here in that thermal belt? Right. The temperature at D is higher because, that is number 4. Temperature at D is higher because of the temperature inversion, which is X. Number 114 is X. Right, what you call a temperature inversion is the reversal of the normal temperature profile in the troposphere. We know well that our temperature profile is negative, meaning to say, as we increase altitude, the temperature must be decreasing. But when we have an increase of temperature with height, that is now what we call a temperature inversion. It's now a reversal of the normal temperature profile in the troposphere. So that is the situation there. Our temperature is lower here, but as we go up, we expect the temperatures to keep on dropping. But in this belt here, the temperature increases because of this belt of warm air, which is trapped. So instead of the temperature decreasing with height, it actually increases in this belt with height, which is a situation of the temperature inversion. All right, moving on to the next question. We're looking at question number 1.1.5. It says frost pockets develop on the dash of the valley. Right, frost pockets, obviously, they occur in the valley floor, which is X. Our frost pockets, they develop on the floor of the valley. Right, we tend to find that our frost pockets, there is accumulation of ice on the valley floor, what we call the frost pockets. That is when the temperatures are excessively low and below freezing point, the moisture in the air will freeze to form pockets of frost, which we call the frost pockets. Right, moving on to the next question. It says, the direction in which the slope faces in relation to insolation, that is what you call aspect of slope or slope aspect. We're looking at the direction which the slope faces. We say in the southern hemisphere, north-facing slopes, they receive more insolation and they are warmer, that is with slope aspect. And south-facing slopes are cooler because they receive less insolation, that is with slope aspect. Right, move on to the next question. The form of precipitation that could occur at the bottom of the valley when temperature drops below 0 degrees. Temperature drops below 0 degrees Celsius. We are saying the temperature here is dropping below a freezing point. So whenever we have temperatures dropping below 0 degrees, we have frost forming in that respect. Right, moving on to the next question. Dash fog may form in the valley on clear, calm nights. What kind of fog forms when we have clear, calm nights? That is radiation fog. Radiation fog is caused by excessive long-wave radiation or terrestrial radiation. When we have excessive loss of heat from the surface during cloudless nights. When we have cloudless nights, we have excessive long-wave radiation because remember, it is the clouds responsible for sending back the heat. That is why we feel warmer when it's a cloud night. But on clear nights, you tend to find that it is very cold, especially in winter. If you check when it's cloudy during a winter night, it's warmer than when it's clear during the winter nights. It's because the clouds will assist in sending back the heat, which is being lost through terrestrial radiation. But when it's clear, it means the heat is effectively lost into the atmosphere and the ground temperatures become excessively very low. Right, we're moving on to the next question. We are looking at the multiple choice question. The first question is saying, the system deflects mid-latitude cyclones away from the coast in summer. It deflects the mid-latitude cyclones away from the coast in summer. What is that system? Basing on this, the coastal low, we know that the coastal low, this is a low pressure cell that occurs along the coast or that occurs at the margin of land and water along the shoreline. And they happen to exist from the western coast going to the eastern coast along the coast, and they'll dissipate in the east around Mozambique there. Definitely this is wrong. The South Indian, when you're talking of mid-latitude cyclones, we know that the mid-latitude cyclones, their movement direction, they move from the west going to the east. So there's no way we can have the South Indian high blocking mid-latitude cyclones from reaching the coast in summer, because already they would have affected, because the South Indian is on the extreme east. So there's no potential of South Indian being correct. The correct response is South Atlantic high pressure cell. Because of the existence of the South Atlantic high pressure cell, it tends to block the movement of the mid-latitude cyclones to the interior in summer, because also its position. Remember we said with the movement direction of our subtropical anticyclones, they move latitudinally with the movement of the ITCZ. So it implies that during the summer season, let me give an illustration. Right, so we are saying with our mid-latitude cyclones, they move from the west going to the east. So let's assume this is our Southern African subcontinent, something like that, right? So we are saying if this is our Southern African subcontinent, we are implying that in this respect, our mid-latitude cyclones, make a clear illustration, right? We are saying if this is our Southern African subcontinent, right? We are saying our subtropical anticyclones, they have a tendency of movement of latitudinal shift, and they move with the ITCZ, right? We are saying if it is summer in the Southern Hemisphere, it implies that our ITCZ is further east to the south of the equator. Let's assume our equator is there at 0 degrees. So our ITCZ is somewhere around this area here. So we also tend to find that our subtropical anticyclones, we have the South Atlantic high pressure and we have the South Indian high pressure. Right. When it's summer, they also move latitudinally with the movement of the ITCZ going to the south. And when it's winter, our ITCZ shifts to the north of the equator, and they will also shift latitudinally with the movement of the ITCZ. So the tendency here is, if it is summer season, they will tend to block the movement of mid-latitude cyclones not reaching the coast here. Right, that is why we only have mid-latitude cyclones affecting the western coast of South Africa in winter season. We're not in summer season because it will be blocked by the presence of the South Atlantic high pressure cell. Right, let's go on to the next question. The next question is saying dash results in stable, fine weather with clear skies. Right, clear weather with fine skies, we find them typically associated with anticyclones. And what we call the anticyclones here, we are saying the anticyclones are high pressure cells. For example, if we have the Kalahari high pressure cell over the interior, if it's there over the interior dominates during the winter season, we know very well that during the winter season, we have fine weather, we have clear skies. Because there is strong sinking air, the air will be sinking such that there are no tendencies of cloud formation. Clouds can only form if the air is rising or is ascending. But if the air is sinking, it means we have clear skies and fine weather. It's typical conditions associated with the anticyclones or the high pressure cells. Right, we move on to the next question, which is number 1.2.3. Right, for 1.2.3, we are saying in winter, dash air compresses and dash adiabatically, which causes the invasion layer to be below the escarpment. We are looking at this situation of the escarpment and the invasion layer. Right, this is the interior, and this is the coastal area. Right, so we are saying in winter, dash air compresses. What kind of air compresses? Is it sinking air or rising air? Definitely it's sinking air that compresses and dash adiabatically, which causes the invasion layer to be below the escarpment. If air is sinking, there's strong descending air, and this air definitely is going to force itself down the escarpment. If the air is sinking down the escarpment, is going down the escarpment, we know well that there is a concept of adiabatic heating. The air will heat adiabatically. We are saying if the air is heating adiabatically, is being heated without the influence of the external environment. It heats up internally because of changes in pressure. The air molecules are exposed to more pressure as they sink down, and because of the increase in pressure, there is limited space. And with that limitation of space, it means the average temperature of the molecules is going to increase because of the reduction of the space which the air molecule is occupying. So as a result, we tend to have adiabatic heating happening because of that situation. So we have item 1 and item 3. So our correct response is item 1 and 3, which we find at A. That is our correct response for that particular question. Right, moving on to the next question, number 124. In a thermal law, the air in contact with the surface dash and dash towards a low pressure sender. Right, we want to analyze that response and see how the correct responses can match. Right, in a thermal law, we are looking at a thermal law situation here, which is typically summer conditions over the interior. When we have intense heating during summer season, we tend to have a low pressure developing over the interior because of the intense heating or insolation which that happens during summer conditions. So in a thermal law, the air in contact with the surface dash, the air definitely heats. The air heats, it does not cool because we have intense heating. The air which is in contact with the surface is heated by the long wave radiation coming from the surface because the surface is receiving insolation from the sun. So our first response here in relation to the air is the air heats. Right. We need to analyze the next statement of our response. And dash towards a low pressure sender. How does the air react towards a low pressure sender? Towards a low pressure sender, if we have a low pressure sender here, the sender of a low pressure cell, how does air relate to this? We know that air moves into the center of the low pressure. And as it moves, we are saying the air is converging. Divergence is the opposite. When you have a high pressure cell, air tends to circulate out of the high pressure cell. Typical of what we call divergence. The air is moving out, is moving away from the center of the high pressure cell. And also remember the circulation direction. If we have a low pressure cell, air feeds into the low pressure cell in a clockwise direction. And in the southern hemisphere, if air is being driven out of a high pressure cell, it drives out in an anti-clockwise direction like that. Those are the circulation cells. So our correct response is matching item number 2 with item number 4. That combination, we find it at item D. So this qualifies to be the correct response. We move on to next question, number 125. Onshore winds on the west coast are dash with dash. The onshore winds you are referring to the winds coming from the ocean onto the interior. And we are looking at the western coast here. Remember, on the western coast, we are saying this is our southern African subcontinent. Our west is here, our east is here. This is the Atlantic. And this is the Indian. Right, so we are saying onshore winds from the Atlantic. What kind of winds are they? Right, automatically we know that this is a cold ocean because of the cold ocean currents, the Benguela, and this is a warm ocean. Because of that reason, we are saying the air is cold. And in terms of moisture content, it will be dry. Cold air has no capacity to contain moisture, but warm air is the one that has capacity to contain moisture. So when the air is cold, automatically it means it's dry. Right. Then with what kind of moisture does it have? Is it no moisture or is limited moisture? It's limited. It has very limited amounts of moisture. It has limitation in terms of moisture content. So the matching response is item 2 and item 4, which we find at response number D. Right, let's quickly move on to the next question. Right, number 126. 126 is based on the plateau against the coastal area with air subsiding over the escarpment. Right, name the pressure cells at A and B as indicated on the diagram below, which is responsible for the development of Berg winds. Right, we want to look at those two pressure cells which are responsible. At A, we are seeing that there is subsidence here. There's descending air, there's strong subsidence or strong descending air. This is typical conditions caused by the Kalahari over the interior. And this is typical of the Kalahari dominating during winter season, creating high pressure over the interior here. And these high pressure winds, which are being compressed down, are going to be driven by pressure gradient because there will be a low pressure around this area. And definitely this is a coastal low, which happens along the coast. So there's pressure gradient, there's high pressure over the interior and the plateau, and there's low pressure around the coastal area. And because of that, it facilitates the air to move from the interior going towards the coastal area. And as the air goes down the escarpment, it heats up adiabatically. And as it reaches the coastal areas, it becomes a hot and dry gust wind with the form of the Berg wind. So our correct response for number 126 is a combination of Kalahari and coastal low, which is our correct response for number 6 is item B. Right, we move on to question number 127. South African Berg winds are warm offshore winds due to the dash. Right. Why are South African Berg winds warm offshore winds? Due to what causes that? If we check, it says temperature they are warmer above the plateau, which is wrong. Low pressure cells that needs warm moist air from the interior, that is wrong. Temperature of air that decreases by 1 degree Celsius per every 100 meters as it ascends. No, this is wrong. And the correct response is D. Temperature of air that increases by 1 degree Celsius per 100 meters as it descends. Right, we are saying here, for every 100-meter descent, the air increases in temperature by 1 degree Celsius. Let's say the air here is maybe cold is around 15 degrees Celsius. It means for every 100 meters, it gains 1 degree Celsius because of adiabatic heating. After the first 100 is now 16, the next is now 17 degrees Celsius, the next is now 18 degrees Celsius, 19 degrees Celsius. As it gets here, it's around 30 something. It's now very hot and a dry wind. Right, that is how the Berg winds form. That is item D. Right, we go on to the next question, which is a satellite image on mid-latitude cyclones. Right. The first question is saying, let's analyze this. We are seeing this is a typical satellite image. There's a warm front here and a cold front here. Automatically, they are meeting here around A, where there is intense low pressure, and we are seeing South Africa here. Right. So we want to try to analyze the weather system. It says A is dash high or low pressure cell. Automatically at A, that is where the system is circulating from. That means it's a low pressure. So for A, that is a low pressure. It's low for A. Right, give evidence from the satellite image for your answer in question 131. Why did we say it's a low pressure? Right, for obvious reasons, it means it's in the center of the system. The center of the system, we know that it's a low pressure at the center of the system. I'll just indicate the responses here, right? We are saying it is in the center of the mid-latitude cyclone. We are seeing that this is the center of the system. There's a warm front stretching to this side and a cold front stretching to that side. This automatically becomes the center of the system, of the weather system. Or why are we saying it's a low pressure? We can also argue that we can see that is there's clockwise circulation. How do we see that there's clockwise circulation? We see it's indicated by the clouds. We know well that this weather system, it circulates in a clockwise direction, and in the midst of the weather system, there's a low pressure cell which facilitates the circulation, the clockwise circulation. So automatically A, being at the center of the system and the system is circulating in a clockwise direction, that justifies that the center of the system is a low pressure. Right. And also the other argument that we can use, we can also use the argument that there is condensation, or we can say condensation, or there's cloud formation. We know well that a low pressure system facilitates the upliftment of air and the formation of clouds. We cannot have clouds if we are having an anticyclonic system. If the center of the system was an anticyclonic, it means it was going to give us clear conditions. But because we are having evidence of condensation taking place, because of the formation of clouds that you are seeing there, that white illustration here that you are seeing is in the form of a cloud. These are clouds that you are seeing. So for these clouds to effectively form, it means we have a low pressure system at the center of the system here. We cannot have cloud formation if you are having anticyclonic conditions. Right, let's move on to the next question. The next question is saying, describe the rainfall usually associated with the cloud type at the warm front. We want the rainfall which is usually associated with the cloud type at the warm front. Right. At the warm front, like, let me try to draw a cross section of the weather system. Right. What will happen is the system will be like this, and we are having this. This is the cold front, and this is the warm front. And this is our ground surface, and our west and our east. The weather system, it moves in that direction from west going to east. Right. So what will happen is this is the warm sector of the weather system, and this is called air, and this is cool air on this side. Right. Because of this situation, we are saying the cold front advances more faster towards the direction of the warm front, and the warm front is slower. So because of that reason, we tend to have strong subsidence happening here of warm air, and here there is general upliftment of warm air. The gradient of the warm front is general, if you can see here, but the gradient of the cold front is steep. Right. So which means we tend to have warm air being forced to rise vertically here, creating towering clouds on this side. But the clouds that we find here are not of large vertical extent. They are flat clouds that we find. So because of this reason, this side receives heavy rainfall because there is strong upliftment and condensation and cloud formation happening here because of the steepness of the cold front. There is strong rainfall which is experienced here, but which is short-lived. It's strong and it's short-lived. Why is it strong? It's because there is strong upliftment of air. The clouds form rapidly and condensation happens rapidly, creating towering clouds like the cumulonimbus that produce heavy rainfall. But it's short-lived because of the speed of the cold front. The cold front keeps on advancing, meaning to say upliftment happens in continuous cycles moving towards the east. But here, because of the movement of the warm front, these clouds will tend to produce a rainfall which is long lasting because the warm front is not as fast as the movement of the cold front. So the nature of the rainfall here, because of the nature of condensation taking place, the condensation happens gradually, meaning also to say there is light rainfall. So here on this side, we have light rainfall. It's not heavy, it's light on this side, but also it's continuous. It lasts longer. It's light rainfall on this side, and which is continuous. Here, it's strong rainfall, which is short. So our question is actually looking at this side. So our correct response is light rainfall, which is continuous on this side of the warm front. Right, moving on to the next question. Right, it says, give a reason why the interior of South Africa experiences clear skies. Right, from our satellite image, we want to try and figure out a reason why the interior of South Africa is having clear skies. Right. Let's go to our system. We are seeing that the interior of South Africa is here. It's clear. The clouds are further to the south. They are happening over the ocean here. The mid-latitude cyclone is actually moving over this ocean here, while the interior of South Africa is having clear conditions. So why is it that the interior is having clear conditions? When over the ocean we are having clouds forming and unstable conditions. because of the mid-latitude cyclone. So that is number 1.3.4. Right. Why is it clear there? Is because of a well-developed Kalahari high pressure cell. If the Kalahari high pressure cell is well developed, it causes clear conditions. There will be strong subsidence, there will be strong sinking air, meaning to say chances of cloud formation are very limited and there will be clear skies over the interior. Right, that is one dominant reason. And also we can talk of strong subsidence to add to that. If there's strong subsidence, it means there's strong sinking air and ultimately we cannot have cloud formation. That is why we have clear conditions over the interior. And also we can talk of sinking air. The same from the Kalahari high pressure cell. If you are having sinking air, we are saying instead of the air being uplifted, it's going downwards. So clouds can only form, or unstable conditions can only result when we have a low pressure cell over the interior, which facilitates the upliftment of air. But in this situation, we are having sinking air, meaning to say we cannot effectively have cloud formation or condensation taking place when the air is ultimately reversing the normal movement of air into the zone of saturation, the zone of condensation, the condensation level or the dew point. So because of these reasons, we tend to have clear conditions over the interior. Moving on to the next question. Right, number 135, it says, in a paragraph of approximately 8 lines, explain how the approaching cold front changes the cloud cover and winds experienced at area B. Right, let's look at area B. This weather system is ultimately will approach the interior. How is it going to cause a change in the conditions over the coastal area here? That is the question. The approaching of the mid-latitude cyclone, how can it cause a change in the cloud cover and winds which are experienced in that area? So I will start with cloud cover. All right. Right. What is going to happen to cloud cover? The first thing that we need to look at here is there will be rapid upliftment of warm, moist air. Rapid upliftment of warm, moist air. And then what is going to happen? Air cools and condenses. Increased condensation results in cloud cover or overcast conditions. Right. So we are saying if the mid-latitude cyclone is reaching the area B, like the cold front you are seeing, the cold front is here, and ultimately is approaching the coastal areas. What is going to happen? The warm and moist air, which is over the coastal area, is going to be uplifted because of the coming of the cold front. The cold, dense air behind the cold front is going to ultimately displace the warm air from the ground surface and is going to be forced to be uplifted. And as it is uplifted, it's going to reach condensation level. And by reaching condensation level, we are saying the moisture in the air, in the rising air, is going to change form. It's going to change form from being water vapor into water droplets, and those water droplets ultimately will result in the formation of clouds, and that is going to change the cloud cover. We are going to have cloud cover or overcast conditions over area B because of the approaching of the cold front. And to be specific, we are going to have cumulonimbus clouds as the cold front approaches. like what I've mentioned earlier, because of the steep gradient of the cold front, ultimately it is going to cause a strong upliftment of the air, and apparently that is going to result in towering clouds in the form of cumulonimbus clouds. Right, that is with cloud cover. Then we also need to look at winds. How is the wind going to be affected at area B? Right, with wind, we are saying strong pressure gradient. Then another point, we can also say right. Strong pressure gradient will cause strong or gust winds. There will be strong pressure gradient there. Behind the cold front, there is a high pressure behind the cold front here, and there will be lower pressure over the interior. So because of that pressure gradient, the approaching cold front is going to cause strong winds. There is a very strong difference in pressure behind the cold front and ahead of the cold front, implying that the winds will be strong and will be gusty. And also, this system, we are saying there's clockwise circulation, the system, and that is also going to influence wind direction. The direction of the wind is going to be affected by the circulation of the weather system. That is how it is going to affect the wind in that particular area of area B along the coastal area. Right, let's move on to the next question. The next question is an infographic on tropical cyclones. Right, we are seeing this is a cross-section of the tropical cyclone, where we have the eye and we have sinking air in the eye. Then on the eye walls, we have upliftment of air and these towering clouds forming. Right. Then we have this, it's giving us the relationship between wind speed and air pressure. There's an increase. Then as you approach the eye, we are saying pressure is higher on the outer part of the weather system, but as we approach the eye of the system, pressure is very low in the center of the system. As we check also, wind speed is lower away from the focal point of the weather system, but as we approach towards the eye of the system, wind speed increases and it reaches maximum, but it drops in the center of the system. Then we also have isobaric representation of the tropical cyclone. We are seeing the isobars indicating pressure, and pressure is ultimately lower at the center of the system and is higher outside of the system. And we also see this is our active quadrant of the weather system indicated by B. Right, let's try to figure out the responses to the given questions. Right. 141. What evidence indicates that the tropical cyclone developed in the southern hemisphere? What evidence do we have here to show that this tropical cyclone is typical of tropical cyclone in the southern hemisphere? Right. If we check these arrows, they are indicating how the weather system is circulating. If you check this arrow that you are seeing here, this arrow and this arrow here is also indicating the circulation direction. So based on this argument, we can safely conclude that it's in the southern hemisphere because the circulation is clockwise. There is clockwise circulation. So our response is clockwise movement of air. This only happens in the southern hemisphere. We have clockwise circulation into the center of the law in this, but in the northern hemisphere is the opposite. So this is typical of southern hemisphere conditions. Give two reasons from the infographic to indicate that the tropical cyclone is in its mature stage. What evidence can we figure out to suggest that this tropical cyclone is in the maturity stage of its position of formation, right? And the other thing also, besides from the previous question, besides the clockwise circulation, there's also another piece of evidence that we can also use to indicate the direction, right? We can also use position of the left quadrant, this thing here. This quadrant is indicating that it's in the southern hemisphere. The position of this quadrant here is also indicating that it's in the southern hemisphere. It's in the left hand, the left quadrant. It indicates that it's typical of conditions in the southern hemisphere. Right. So we move on to the next question. Give two reasons from the infographic to indicate that the tropical cyclone is in its mature stage. What evidence can we figure out to suggest that it has matured? Right. Pressure at the center here. If it has reached maturity, pressure drops to below 1,000 at the center of the system. The pressure at the center of the system will be below 1,000 hectopascals. So if we check here, this is 972, and implying that the interval here is 72, 74, 76. It's 2 hectopascals. It means this one is 970, and the center is slightly lower than 970. So it means this has matured because the center of the system has ultimately had a pressure which is below 1,000 hectopascals. And also, if we check here, this eye here, the eye is well developed. It's another evidence. Well-developed eye. If the system has a well-developed eye, it suggests that it has matured. In its initial stage, the eye would not be very distinct. But when we see the eye being fully developed, then we can suggest that the system has fully matured. And also, if we check our left quadrant here, the left quadrant is visible. I think you can see from this illustration, the shade is suggesting that this active quadrant is very visible and is more pronounced, suggesting that the system is matured. So basically, using that evidence, we can suggest that the area, the tropical cyclone, is also fully matured. And also, if we can also give an argument of the area which has been covered by the tropical cyclone, like if we check here, you can see from the outer part to the center, it's about 450 kilometers. And from here, the eye to the outer part of the system is about 500 kilometers. So it also suggests that the coverage of the area suggests that the area is matured. It's now covering a wider area. As the system matures, it covers a wider area. So this suggestion of the distance covered by the system it suggests that the system has also fully matured by ultimately looking at the area, the spectrum of the area covered by the weather system. Right, we check the next question. How will the descending air at A influence the cloud cover in the eye? We are seeing that in the center of the system here, there's descending air. Yeah. How does it influence clouds formation, or what will it be like in the center of the system? There's descending air. In the eye of the tropical cyclone, we'll have clear conditions. The descending air will ultimately result in clear skies. There will be clear skies in the center of the system. We don't have cloud formation in the center of the system. The weather system will be stable in the center of the system because of that descending air. Or we can say there will be no clouds. Right, number 1.44, it says, give a reason for your answer to question 1.4.3. Why are we saying there will be clear skies, there will be no cloud cover? Right, the reason here is descending air heats up. resulting in no condensation. That is why we're saying there will be no clouds, because of the descending air. Or we can say there will be adiabatic heating as the air descends. Adiabatic heating reduces moisture. As the air sinks, it heats up adiabatically, and that reduces the amount of moisture, and there will be no condensation that will effectively take place, that will effectively lead to condensation. So given the absence of moisture, there is no cloud formation, and apparently there will be no clouds in the center of the system or in the eye of the system. That is why we have clear conditions or cloudless conditions in the center of the mid-latitude cyclone. Right, we move on to the next question. What is the relationship between the wind speed and the air pressure as indicated on the graph? Right, that one there is just an extraction question. We just need to analyze the relationship. A ahead of the eye and within the eye. Right, ahead of the eye, I'll try to give the illustration here. Ahead of the eye, we are seeing here. What is the relationship there? Right, air pressure, we can see air pressure is decreasing and wind speed is increasing. Ahead of the eye, the air pressure is decreasing here. You can see air pressure is decreasing, while its wind speed is increasing. That is ahead of the eye. And within the eye here, what is happening within the eye? We are now in the center of the system. If we check the two illustrations, what is happening to wind speed? Wind speed, you are seeing it's decreasing. And also what is happening to air pressure is decreasing again. So we are saying ahead of the eye, wind speed increases and air pressure is decreasing. Within the eye, both of them are decreasing. Wind speed is decreasing, and at the same time, air pressure is decreasing. That is what happens within the eye. Right, let's move on to the next question. Why is the area B on the sketch of the isobaric representation referred to as the leading left quadrant or the dangerous semicircle? Right, this area here, we call it the dangerous semicircle of the weather system, this one here. Right, it's dangerous in the sense that the air speed or the air movement is strongest in this section of the weather system. And that is where we experience the worst destruction of the weather system. The air is very strong in that area, which we call the dangerous quadrant of the weather system or the active quadrant. Why is it that we have that semicircle on the left being the most dangerous with the highest wind speeds and what resulting in the most destructive effects of the weather system? Why does it appear on that dangerous quadrant? That's the question. Right. What happens with this here? Let me try to make give a response. That is question number 1.4.6. Right, so this area experiences the most intense weather condition. The most intense weather conditions. We can talk of very strong winds. Right, why does it experience? Why is it worst in that area? Right, if we try to check, right, there is combined effect in this dangerous quadrant. We are seeing that the weather system is circulating in this direction. And because of that circulation of the weather system in that direction, we also have the effect of Coriolis. Right. Coriolis effect, we understand in the southern hemisphere, it causes winds to deflect to the left and in the southern hemisphere and to the right in the northern hemisphere. So we are saying there is also a deflective effect which is happening in the same area. Winds are being deflected to the left. At the same time, the winds are circulating in the same direction in this quadrant here. We are seeing that the circulation is going in this direction, while the deflective effect is also going in the same direction. So the combined effect of deflective effect of Coriolis combined with the circulation of the system creates very strong winds in this area. Because if we try to check in this area, why is the dangerous quadrant not in this area here? It cannot be in this area because what is only affecting here is the circulation of the weather system. Deflective effect is going in the opposite direction. They are not going in the same direction. Deflective effect is going to the left, while this system is going in that direction. So there is no correspondence of Coriolis and the circulation of the weather system, but they can only correspond and work together in this quadrant here. The weather system is circulating in this direction, while Coriolis is also acting in that direction. So the combined effect of Coriolis deflective effect with the circulation of the weather system gives very strong and intense weather conditions in that quadrant that we call the active or the dangerous quadrant of the tropical cyclone. Right, I'll move on to the next question. Right, how does the leading left quadrant dangerous semicircle develop in tropical cyclones? I think I have ultimately answered that question. It says, how does the left hand quadrant? Right, I've answered that question. The response that you can have here is the forward movement combines with the rotation. Right, I'll move on to the next question. Refer to the fig below on urban heat islands. Right, that is an an illustration of urban heat island. It says little vegetation or evaporation causes cities to remain warmer than the surrounding countryside. Right. Question number 151. It says define the term urban heat island. Right. How can we best define an urban heat island? Right, when we're talking of an urban heat island, we are looking at a situation whereby we have an urban area that has got higher temperatures compared to the surrounding rural areas or the surrounding farmland. An urban area having a higher temperature compared to the surrounding rural areas. Right. You must not confuse those two concepts. Usually tend to find that there is a confusion between an urban heat island and a pollution dome. Must not confuse those two. An urban heat island, we are talking of temperatures here. So we are saying an urban area having higher temperature compared to the surrounding rural area. That is the situation of urban heat island. It's an heat island in the sense that there's higher temperature in an urban area compared to the surrounding rural areas. State one factor that makes urban areas become warmer than rural areas. What contributes to higher temperatures in the urban area compared to the rural areas? Right, number one is little vegetation. We know that vegetation has a cooling effect. So because of limitation of vegetation, we tend to have higher temperatures in the urban area. Or we can also argue that it's higher because of artificial surfaces. We can give examples, e.g. tarmacs or concrete surfaces. They tend to absorb more heat. We have more of artificial surfaces in urban areas than in rural areas. So as a result, we tend to have higher temperatures in the urban area. And also we can look at volumes of vehicles. In the urban area, we tend to have more vehicles that release pollutants that tend to absorb heat in the urban area. So among some of those reasons, you can argue, or you can also argue on appliances that cause heat, that generate heat, or you can talk of industries that produce heat. So those are some of the contributing factors why we have higher temperatures in the urban areas compared to the rural areas. Right. Account for the fact that it says explain how urban activities increase temperatures in the city. Basically, these are some of the responses leading to that. We can talk of vehicles. We are now giving details. What do they do? When there is vehicle presence, it ultimately results in pollutants. And the pollutants, they absorb heat. You can look at industries that produce heat. It's also another activity that happens in the urban area. Then account for the fact that the city receives more rainfall than rural areas, even though more evaporation takes place in the rural areas. Why do cities receive more rainfall? The argument here is the presence of what you call hygroscopic nuclei. Nuclei, or what we call the nuclei for condensation. Condensation nuclei presence. Right. For effective condensation to take place, we need what you call the nuclei for condensation, or what you call the hygroscopic nuclei. So in urban areas, because of the levels of pollution, there are so many particles in the atmosphere, like dust particles. Those particles, they facilitate condensation. Condensation needs some form of nuclei for it to happen. So in rural areas, because mainly the air is clean and there are no particles in the atmosphere, even though there's high evaporation, but the effectiveness of condensation taking place is limited because of the absence of the hygroscopic nuclei of condensation. But in rural areas, we tend to have urban areas, we tend to have large volumes of pollutants in the atmosphere, and those pollutants are equally important in facilitating condensation. And because of that, we tend to find that we have high levels of condensation happening in the urban areas because of the presence of the hygroscopic nuclei of condensation. So because of that, we tend to have effective condensation taking place in urban areas because of the presence of nuclei. Right. Let's go. That brings us to the not last question. Discuss how heat islands can affect the health of people. We are looking at this heat island. How can it affect the health of people? The prevalence of high temperatures in urban areas How is it a negative implication on the health of people in urban areas? How is it likely to affect the health of residents of urban areas? Right. Our argument, we can say, because of the high temperatures, it causes heat stress. It causes heat stress because of the high temperatures. People are exposed to the problem of heat stress. It can also cause fatigue, extreme tiredness in the urban area because of high temperatures. And also it can cause dehydration, excessive loss of fluids in the body because of high temperatures. You will be sweating and you'll be losing fluid from the body. And ultimately, it can cause death amongst the elderly. The elderly people are prone to the implications of urban heat islands because of complications in health associated with the old age. They are vulnerable and they can ultimately lose their lives to high temperatures in the urban areas. Right, that brings us to the end of our climate question. We take it on to geomorphology, which is question number 2. Right, our first question is based on the illustration below on drainage patterns. We have pattern A and we have pattern B. Right, if we closely look at these patterns, we tend to find that pattern A is more of a trellis pattern, and pattern B is more of a rectangular pattern. Right, so based on that, we need to relate to the two. Right, the first question, it says, tributaries join the main river at right angles. Right, this is typical of A. We are seeing our right angles. So that is A for the first question. There are right angle bends along the course of the river, of the main river and its tributaries. Automatically, right angle bends, we are seeing them there, we are seeing them there. So that is B. This pattern occurs in folded sedimentary rocks. Typical of A, we find it in folded areas, like we are having a fold here and we are having a fold there. The reason why the tributaries are short is because they are limited by the folds. If this is a fold, it means the tributaries cannot stretch across the fold. They are limited by the fold. And the main river develops in the valley between the two folds. So it's typical of A. Then 214. This pattern occurs in folded. We're done with that. Number 3. Number 4, develops in areas where folds occur parallel to each other. Where folds occur parallel to each other, that is A. Right. Form on rocks that have joins. Number 5, rocks with joins, they give us rectangular pattern, which is B. Tributaries are short, that is automatically A. And tributaries often flow from gaps or from the ports. Right, that is typical of A, like what I've just mentioned there. So those are our correct responses for the first question. We move on to question number 2, question 2.2. Right, it refers to a meander along the river. Right, I'll just try to explain briefly on the meander here. Right, basically a meander is a bend along the river channel. Because of the presence of a bend on the river channel, we tend to find that it affects the flow speed of the water in the channel. Right, like at A here, this is what we call the outer bend of the meander, and at B is called the inner bend of the meander. And here there is less velocity. The water moves slowly because it's forced to bend just instantly. And there is deposition happening because of limited velocity. Deposition tends to happen. On the outer bend here, we have high velocity of water. The water tends to flow fast on this outer bend, and also because of that, there is what we call there is the process of erosion happening, and the slope here we call it an undercut slope, while this one is called a slip-off slope. The slope that develops on the inner band is called a slip-off. There's deposition, water has less velocity, and it's the inner band of the meander. This one is the outer band of the meander. There's high velocity and there's erosion taking place. The nature of the slope is called the undercut slope. That's the summary of the meander, if you are to check those two. Right, let's go to our questions. Right, our first question, it says, meanders generally form in dash course of the river. Definitely meander, we find them in the lower course of the river. Right, deposition occurs at A or B. Where does deposition happen? Like what I've just explained. Right, in that instance, we are saying deposition automatically, it happens at B, like what I've mentioned. It happens at B. Right, river flow is rapid at rapid. We are saying it's fast. It's fast at A. I've indicated that. The river cliff is likely to develop at a river cliff is more or less like what you call the undercut slope. It develops at A. Right, moving on. Number 2.25. B is called the dash slope. B, I've indicated B is the slip off. And A is called the undercut. We have talked about that, right? The meander loop at A is likely to develop into, right? If there's a meander loop, the meander loop is likely to develop into an oxbow lake. Oxbow lakes, they form from meanders, right? A canoeist, a person who paddles on a boat, is likely to favor the bank at A or B. Which bank is likely to be favored? Likely to favor the bank at A. Right. Those are responses to question 2.2. Moving on to the next question. Right, the next question is saying, what evidence suggests that these two fluvial landforms formed in the lower course? We are looking at the formation of an oxbow lake. From a meander, the neck ultimately breaks and the oxbow lake forms. Right, what evidence do we find there which suggests that this landform forms in the lower course? Right, the evidence is that there is flat terrain. In the upper course, we have steep terrain, but in the lower course, we tend to find that the terrain gradient reduces. It becomes a flat terrain. And also, we have evidence of deposition. Deposition in the sense of the sand and the silt, which has been put here. Deposition happens in the lower course. We don't have deposition in the upper course because of high velocity. There is erosion in the upper course, but in the lower course, there's deposition, and the evidence is the sand and silt which has been put on this part, which is now separating the main stream from the oxbow lake. Right, moving on to the next question. Identify the two fluvial landforms in sketch A and B. Right, in sketch A, you can see that automatically in sketch A, our fluvial landforms, in A is a meander. This one is a meander, which is a bend along the river channel. We are seeing the river is bending like this. So the fluvial landform is a meander for A. Then for B, our fluvial landform is now an oxbow lake. So ultimately, an oxbow lake develops from the meander. If a meander becomes pronounced and the river manages to break the neck of the meander, ultimately it becomes an oxbow lake. Right. So how did the fluvial landforms A develop? We are looking at the meander. How did fluvial landform A develop? How does a meander develop? Right. Let me just summarize it like this. There is flatland, which leads to less velocity. Then, as a result of that, there's lateral erosion. deposition on inner bank. Right. So ultimately, how does the meander form? A meander forms because of the terrain being flat. The area is flat, implying that the water velocity, the flow velocity of the stream becomes less. And as a result of that, we tend to find that there is lateral erosion taking place. There is sideway erosion that happens to take place, creating the bends. And as there is a bend on the river, we tend to find that the velocity of the water will tend to differ now, causing erosion on the outer bend and deposition on the inner bend. And that will continuously happen until the meander becomes more pronounced. The bend becomes more pronounced because on one side it's eroding and is depositing on the other side. Why further winding the bend along the river channel. That is basically how a meander forms. Right, moving on to the next question. Discussed, we have talked about that. The formation of landforms, discuss the formation of fluvial landform B, right? Basically an oxbow lake. Like what we are seeing here, I'll use this explanation. Right, we are seeing how an oxbow lake forms. It starts from a meander, that's the first step. And on the meander, we have an outer bend where there is erosion. And here there's deposition. The same happens on this bend. This is the outer, there is erosion, and there's deposition on the inner bend here. Because of this, we tend to find that this bend advances in this direction, while this also advances in that direction because of erosion taking place and erosion taking place on either side until the river manages to break the neck here. If the river manages to break the neck, it means the river now takes a straighter course now. And because of this now, there is deposition that is going to happen here. Deposition is going to happen and ultimately blocking the oxbow lake from the supply of water from the main river. Now the river takes a straighter course, while this remains as a lake on its own, independent from the river, which has managed to break its course through the bend. So basically, the oxbow lake originates from a meander. The outer bend of the meander is undercut and is eroded. This makes it advance towards the other outer bend of the meander until the two reach each other and manage to break. The river manages to break through and takes a straighter course, like what you are seeing here. The river now is taking a straighter course, and there are deposits of sand and silt here, ultimately breaking away the oxbow lake from the main stream. Right, then explain the impact of fluvial landform B on farming activities. The impact of an oxbow lake on farming activities. How does an oxbow lake impact on farming activities? Right, basically it's a source of water, the oxbow lake. You can say it's a source of water, supply water, source of water for the farmer in terms of livestock or in terms of irrigating crops. It's a source of water for that purpose. But however, it dries up to form a meander scar. And what's the implication? The implication is that there will be reduced amount of water to the farmer. The oxbow lake gradually will dry up because there's no more supply of water to this part here because it has been sealed off from the main river. So initially it acts as a source of supply of water to the farmer for both irrigating crops and also for livestock. But with time, we tend to find it dries up and it becomes a meander scar, which is ultimately giving a negative implication on the farmer. There will be reduced amount of water availability for the farmer. Right, that is with question 2.3. Let's move on to the next question, 2.4. Right, it talks about stream piracy or river capture. Right. What is river capture? When you're defining river capture, talk of the energy of the river. It's a process by which A more energetic river it intercepts the headwaters of a less energetic river. Right, a more energetic river, we are saying that the river is strong in headward erosion. It erodes headwardly towards another river and it manages to intercept the headwaters of the less energetic river. That is the process of river capture or stream piracy. Right, how does the gradient in sketch X past cause the river capture? The gradient in sketch X. Right, what is the implication there? A river flowing, for stream piracy to happen effectively, we are saying a river flowing down a steep slope erodes faster and is more energetic. Right. If this river is flowing over a steeper part of the watershed, in this watershed here, is flowing over a steeper part, this one is flowing over a gentle part, it has more energy to erode headwardly. If it's flowing over a steeper gradient, it has more energy to cause headward erosion and ultimately is able to cut through the watershed to intercept the headwaters of the less energetic stream. So that is how gradient influences. If there's a steep slope on the side of the watershed, that river becomes more energetic and it has high erosive power, and ultimately it is going to erode through the watershed until it reaches the less energetic river, and it will be able to intercept the headwaters of the less energetic river. Right, then the next question says, identify the streams A and B in the sketch. Why after river capture has taken place? Right, these two streams after the river capture has happened, we have what we call the captor and the captured stream. So in this instance, our A is the captor, the one that intercepts, and the one which is intercepted is the captured. So our A is the captor stream and our B is the misfit stream. Is the captured one, which now becomes the misfit stream. Misfit in the sense that it has been misfitted from its original supply of water. It was initially getting its supply of water from upstream here, but now it has been misfitted. So it becomes a misfit stream. It's the one which is captured and it becomes a misfit stream. Right, let's move on to the next question. 244. How would the physical or natural environment negatively be influenced by stream B? This stream B here, now there's less water flowing in stream B. How does that affect the natural environment? We are looking at the natural environment here, right? We can talk of disruption of ecosystems. Mainly the aquatic ecosystem is going to be disrupted because of limited supply of water in that stream downstream. And also biodiversity, the variety of animals and plants. Biodiversity will decrease in that area because of limited amount of water. Size of drainage basin would decrease. Drainage basin will decrease. And also, there will be increased deposition because of less velocity of the water. There will be increased deposition in the stream. on the banks of the river. The beauty or the aesthetic beauty of the landscape will diminish. Those are some of the implications on the environment because of stream piracy happening, and apparently because of loss of water in stream B because of stream capture, which has happened upstream. Explain the physical or natural changes that stream A will undergo after river capture. We are looking at stream A, which has managed to capture the headwaters of the other stream. What is going to happen? What are the changes, the physical changes that are going to happen to that stream which has taken or which has robbed water from the other stream? What are the changes that are going to happen to that particular stream? The physical changes, right? The first physical change, which is definite, is volume of water will increase. Because it's now having extra supply of water, its volume of water would increase. And besides the volume of water, we also look at the velocity. The speed at which the water is going to flow would also increase. Because of increased discharge, the velocity is also going to increase. And there will be also increased energy. The river will have increased energy to erode. There will be more erosion taking place because of extra energy which has been gained from extra discharge from the river which has been captured. And also, the river will rejuvenate. River rejuvenation will take place. And the size of the drainage basin will increase. Size of drainage basin will increase. Right, those are some of the changes that are going to happen in that river because of the changes that would have happened with stream piracy. Those are some of the physical changes that we can find in the capture stream. Right, that takes us to question 2.5, which is a case on the pollution of Jukskei River. Right, we got the questions. The first question is saying, define the concept of river management. This is a geographical concept that you can define in many ways, but as long as you're addressing the concept. So here, how I can define, we can say is the process of sustaining and maintaining rivers, and sustaining and maintaining water resources and drainage basins to ensure availability of clean, safe water. And also can talk of aquatic life. So when you're talking of river management, we're looking at sustaining and maintaining water resources in drainage basin with the aim of ensuring the availability of clean and safe water for consumption and also for sustaining aquatic life. That is basically the idea with the river management. Right, the next question says, identify a cause of pollution from the extract. Let's go to the extract. Pollution in the Jukskei River is multifaceted. Generational problem influenced by population expansion, right? So, illegal dumping, overwhelmed service providers, and insufficient infrastructure. It also talks about raw sewage. So we find that these are the causes of pollution from the extract, we are finding that it talks about population expansion is one cause, illegal dumping is another cause, overwhelmed service providers, and also insufficient infrastructure, and also sewage. These are the causes according to the extract. We just extract the evidence from the sources given. Right, moving on to the next question. That is question 2.5.3. It says, quote evidence from the extract which shows that there is an attempt to try at river management by people living near Jukskei River. Right. If we check in our evidence that we have, we tend to find that it says leaks from townships, even from sewage leaks from hijacked buildings in Marlborough South. People often see trucks from construction sites in Sandton illegally dumping rubble on the river banks. Water is our oldest resource, says Paul Maluleke, a volunteer with Alexandra Water Warriors, who are now deploying a nifty device they call the pollution trap to snare sewage and plastic in the Jukskei. So this one here is an attempt. That is an attempt at river management. They've implemented what they call the pollution trap. So the pollution trap, that is the quote that we want in that extract to suggest that they've tried to manage Jukskei River, the pollution trap. And it also says, on World Water Day, we helped to install a floating trap made appropriately of large water bottles tied with a wire. So it's another attempt here. On World Water Day, we have helped. This is another attempt. So we have two attempts there that we can quote, the pollution trap and also this, which they tried on the World Water Day. Right, explain the importance of river management and drainage basin management. Why is it important that we manage rivers and we manage our drainage basins? Right, there for obvious reasons, we need water for the different purposes. If you don't manage our rivers, it means you're going to have insufficient water for the different uses. So we need water for irrigation, for domestic use, irrigation, and other uses. That is why it is important for us to manage the rivers. If we can't manage the rivers, then where are we going to get the water for those purposes? And also, it's expensive to purify water. We must not make our water sources dirty. It is going to be a cost on us to purify the water once it is dirty. It's very expensive to purify water. We can talk of waterborne diseases, which are a threat to life. Consuming polluted water will result in waterborne diseases. For example, we can talk of cholera, which is a threat to human life. So we must not pollute water bodies. And also, we can argue that many people don't have access, do not have access to tapped water. And hence they consume water from the natural sources. So we must not pollute the natural sources, because some people who cannot access tapped water, they need to access water from the natural reservoirs and the natural reserves of water, so that they can consume healthy and safe water. Right, we'll move on to the next question. In a paragraph of approximately 8 lines, discuss the challenges that poor river management will have for the people living along river banks, e.g. the Jukskei River. It suggests sustainable strategies that may be implemented to preserve their drainage basins. Right, if we look at that question, we are trying to analyze the challenges that are typically faced by people who stay along the rivers which are being polluted. What challenges do they face, and what can we do as management strategies to try and deal with the problem? So let's start with the challenges. Right, the challenges that people face who stay along the rivers, we talk of spread of diseases, spread of waterborne diseases. It's a challenge. They are prone to the spread of waterborne diseases because they are staying close to the rivers. And also the other challenge is there's more money needed to purify water. They have that challenge, water becoming expensive because it needs to be purified to remove the pollutants. And also these people, they have to travel long distances to access clean water, which is also a cost for people to travel long distances to access clean water. And then what can we do? What are the strategies that can be implemented to try and solve these problems? Right, we can talk of awareness campaigns. People must be made aware through awareness campaigns so that they don't pollute the water resources. We can use awareness campaigns, or we can use education, educating the people on the need to safeguard their water resources, or we can also use heavy fines to polluters. Like, for example, those trucks which are seen dumping waste in the river, they must be imposed heavy fines on them. And also we can apply buffering. We put boundaries along the water resources or along rivers to limit the influence of people on the rivers, or avoiding settlements close or along the rivers is also another strategy that can be put in place. So given those strategies, we can try to manage and sustain our water resources. That takes us to the end of our section on geomorphology. Right, the last part that we need to look at is map work, but unfortunately, I don't have this map at my disposal. I will just highlight on some skills that you need to have in terms of map skills and map calculations, and also interpretation of map information and GIS. Right. The next question is saying, the feature located at grid reference, you must be able to read your coordinates from the map. Remember, the degree value is provided for you, and also your minute value is provided for you on the map. What you need to do just is to estimate the second value. If it's 32, it means it's slightly in the middle of the block in terms of latitude, then 29, longitude 27, 47 minutes, and 22, it's slightly below the half mark of the line of longitude. So you can just check and be able to figure out among us this, is it a cultivated land, is it Harry Smith, Newcastle, or Colenso? Right. Then the length of area covered by the orthophoto on the topographic map is a dash in kilometers. The area covered by the orthophoto on the topographic map. What you need to note there is you check for the red demarcation, the red demarcation on the topographic map. That is the area of the orthophoto. It will be written there. You check for the red demarcation, the demarcated area, the red block on the topographic map is the one that is used to, is the area which is mapped on the orthophoto map. So you're supposed to find out the length of that area, which means the longer part, the longer side of between the two. You measure and you convert it to kilometers. What you need to do there is your measurement. For you to convert to kilometers, the scale is 1:50,000, remember, for the topographic map. So your measurement in centimeters, you multiply it by 0.5 kilometers. You get your answer directly in kilometers. That is how you calculate that one. Right. We'll move on to the next one. It says, calculate the current magnetic declination of Flat Smith on the topographic map. You are supposed to use the map information to calculate the current magnetic declination. You use the map information and you follow the steps of calculation using the mean annual change of 8. So from the year on the map, you need to calculate the difference in years from the current year minus the year on the map. Then you need to get your total change. You multiply that by the number of years, the mean annual change by the number of years. You follow the steps of calculations. Then calculating gradient between trigonometrical station 325, B2, and trigonometrical station 333 in block C4. Right, what you should note there is on a trig station, there are two numbers. If you find that is 325, and then there's another number with a decimal, that is the height that you use. Use the one with a decimal. You don't use this one, it's a station number, 325. And also you don't use this 333, it's a station number. Use the other figure. There are two figures on the trig station indication. Use the one with a decimal. Subtract the smaller one from the bigger one to get your vertical interval. Then the horizontal equivalence is already given for you. You multiply it by the map scale to convert this distance to meters. Because your height will be in meters, whatever height you are going to figure out from the trig station indicated there will be in meters. So you subtract the smaller from the bigger one, you get your horizontal equivalence is given, you get your vertical interval. The vertical interval is the distance, the difference between the heights of the two stations. Then the horizontal equivalence, you multiply this 5.4 times 500 meters to get your height in meters. Then you express your vertical interval in meters over your horizontal equivalence in meters. And you reduce that to a ratio with a numerator equal to 1, meaning to say it will be 1:2 something. That will be your gradient. Then the next question is talking about temperatures. Temperature at F in the center of town is 2 degrees higher than at G. Name the concept. The concept of an urban area having a higher temperature is the urban heat island automatically. So if you check that area and if it's an urban area and the temperature is higher in the center of the urban area compared to the surrounding rural areas, that is the concept of an urban heat island. That is application of climate to maps. So the concept there will be a concept of an urban heat island. Right, give one reason why high density of buildings at F generally contributes to higher temperatures. Why? Give reasons why high density. Right. The high density of buildings will mean that heat will be trapped. They will trap heat. So heat will be trapped because of the high density of the buildings. They tend to trap heat. And also there's reduced airflow. Air cannot flow effectively because of the high density of buildings. And also we can argue that there is artificial surfaces. Those buildings have got artificial surfaces which tend to absorb heat. And also the other argument, you can also argue that there will be multiple reflections. Glass surfaces or shiny surfaces, they tend to reflect and they reflect back on the other side. So as a result, we tend to find that the temperatures in the urban areas, they will be higher because of the multiple reflective effect caused by the buildings. Right, then the next question is saying, explain how aspect of slope determined the location of Rose Park at 7 on the orthophoto map. When we talk of slope aspect, we are looking at the direction at which a slope is facing. So basically you need to check if that slope is facing to the north or to the south. Automatically, north-facing slopes in the southern hemisphere, they are warmer and they get more insolation. And if a south-facing slope, automatically it means it's has less insolation and it's cooler. So for a park, most obviously, it must be facing to the north to allow for warmer temperatures or to allow for insolation. Right, number 324. A weir is used to regulate or control the flow of water in a river. Explain why the construction of a weir was necessary. Right, a weir is actually necessary because it reduces the risk of flooding. Reduces the risk of flooding downstream. If you have a way, it controls the amount of water and ultimately reduces the risk of flooding downstream. Right, refer the section of the Klip River from 8 block. Unfortunately, we don't have the map. Identify the fluvial feature. You check the fluvial feature on that part of the map, which is asked. And mainly, they ask on features like the meanders along the river. You're supposed to figure it out. If there's a bend there, automatically it means that qualifies to be a meander along that river channel. And then give evidence for your answer. Why it developed in this area. If it is a meander, then you talk about the river being in the lower course, and also you talk about the gradient being flat. Gradient being gentle, and also you can talk of the area being in the lower course of the river. Right, then refer to the orthophoto. Why will more erosion take place at 11 than at 10? If that is a meander, you explain on the undercut. The undercut has more erosion. Why? Because there is high velocity of water. The high velocity is going to cause more erosion. So the outer bend, if it is the outer bend, it means there will be more erosion. And if it is the inner bend, there will be more deposition. And why there's more deposition is there is less velocity of water on that part of the river. Right, then we go to GIS. The vertical aerial photograph used to make orthophoto maps. Yes. Is it a high or low resolution? Right, definitely orthophoto maps are made from high resolution images. They are more clearer. We can actually see the features. We can actually see all the geographical features on the orthophoto map because they were made from aerial photographs of high resolution. When we're talking of resolution, we are looking at the amount of detail in an image, or high resolution, talking in terms of pixels. A high resolution image has got more pixels, or has many pixels, and the pixels are small. While a low resolution image is the one that has got less pixels and bigger pixels. This gives us a blurry image. It has less detail. It's not visible. This one here gives us a clear image. So that is with resolution. So it's a high resolution. Give a reason for your answer. Why are we saying so? Right. The reason is they are clear. Or they have detail. Orthophoto map show detail. You can actually see the details. You can actually see all the geographical features. They have detail. Then the next question is saying, define the term buffering. When we're talking of buffering, we are looking at the concept of demarcating an area or putting a boundary. Demarcating or putting a boundary along or around a geographical feature. That is the concept of buffering. When we're buffering an area, we're putting a boundary, or we're putting a demarcation. We're putting a boundary around a feature. For example, a river. We want to buffer a river. We can put a fence around the river to stop human influence on the river, or we can plant trees along the river as a way of marking a boundary of where human activities must end and not influence the water quality in the river. Then it says, last question, how would buffering at 12 protect the quality of water in the Klip River? How would buffering protect the quality of water? Right, the concept of buffering, we are saying we are putting a boundary around the geographical feature. In this instance, we are putting a boundary along the river. How would that protect the quality of water in the river if we put a boundary or you put a demarcation along a river? How would that protect the quality of water? So it will restrict development on river banks. It means if you put a boundary, people cannot do development on river banks, and ultimately that is going to protect the quality. Or it will decrease pollution. Definitely from surrounding areas. If there's a boundary, then people cannot go and dump waste into the river. That will result in decreased pollution of the river. And also, it will decrease eutrophication. The disposal of fertilizers into the river, causing the excessive growth of algae in the river, is going to be limited because of buffering or putting a boundary along the river. And also, we can talk of reduced salinity. The addition of salts in the water is going to be limited, and ultimately the water quality is going to be good because of the boundary that would have been put around the river. So if we check around those arguments, that can be detailed arguments towards the sustenance of water quality because of the application of buffering in the river. So basically, that was the end. That was the last part of our paper. That was the last part of our discussion, and that takes us to the end of this discussion. So I hope this discussion is going to assist you in your preparation for the exams, either the June exams, the prelim, and ultimately your final examination. So that brings us to the end of our discussion. We will meet in other discussions to follow. Thank you for watching.